Thank you so much. Am I audible? Hello, am I audible?
Yes, I'm here.
Yes, we can hear you, but not very clear.
Okay, I'll try to be a little better. Good morning, good afternoon, and good evening from different parts of the globe. First of all, I would like to thank organized committee for providing this platform to share my research work. I'm Durga Khanal from Nepal. I am the PhD student of Tribhuvan University under the supervision of Dr. Pyakurel and Dhamala. My topic of presentation today is prioritize multi-commodity flow model and algorithm. These are the outlines of my presentation: motivation, intents of prioritization, literature review, problem statement, and solution strategy. These are some motivational pictures taken from Google. These are all natural disasters. Disasters may be natural or man-made, but after disaster or pre-disaster, disaster management is very essential. So we are going to present here this work about post-disaster management, and without well preparedness, efficient planning, efficient way to work efficient way, it is very essential to prioritize the work. After the disasters, every individual may not be hurt equally. Some people may get injured, some minor injured, and some of them may not be hurt physically. Who are critically injured have to send well-equipped hospitals, like minorly injured can send into private health centers. Old age people, disabled, pregnant women with babies, that can be sent in care centers, as well as normal cases we can send in safe centers. So these all are the prioritization of source as well as sink. The importance of prioritization are as follows. Like prioritization means deciding the relative importance of objects which emphasize to achieve the objective goal. It is applicable for large-scale disaster management problem, and this prioritization work, what we have studied, is on the basis of case sensitive. According to the case, the treatment or a case of the injuries, different places should be sent. So it is case sensitive way of study. And our model is multi-commodity flow model. In multi-commodity flow model, multiple commodities are present, and they are from respective sources to corresponding sinks without violating capacity constraints on the arcs. These are some literature reviews. The pioneer of network optimization are the Ferguson, the max flow problems, minimum code, quickest flow, time extended network, temporary repeated flows, and many more we can find in their books and articles. In 73, Mineta has given maximal lexicographic static flow problem. They have studied about the multiple source or multiple sink. In 74, Mexico has given lex-max static flow problem in single source and multi-sink network. Similarly, in 7, Hamaka and Feki have given lex-max lexicographic mean cost flow problem for evacuating the people from a building. They have divided a building into different categories or sections, and All these sections are prioritized, and according to the prioritization, they have evacuated the people. Hope Cardos have given polynomial time algorithm for lexicographic maximum dynamic flow problem. For the multi-commodity flow problem, Fisher and Iskutala have given flow over time, that is dynamic problem in multi-commodity case. In Pyakurel and Dente in 2020 recently, they have studied about maximum dynamic contraflow with intermediate storage. This is the sample of the network model. This is multi-commodity network. Multi-commodity means we are taking care of multiple commodities. In this example, we can see 3 commodities are here. Commodity 1 transit from S1 to T1, as well as commodity 2 from S2 to T2, and commodity 3 from S3 to T3. We denote the network by N. The component inside V is a set of vertices, A for set of arcs, K is the set of commodities we use here, U is the capacity of arc as seen in the figure. The numbers indicate the capacity of the arc. GIs are the net flow of the commodities, and S and D are the set of sources and sinks respectively. The problem statement is as follows. For the given network N, which is a multi-commodity network, and with prioritized order Pi, precise Pi plus 1, then prioritized multi-commodity flow problem is to transfer the net flow GI from Si to Ti by using priority ordering function and without violating the capacity constant on the arcs. Here, this function, prioritized function P, is a quantity prioritized function from K to Z plus. K means commodity, Z plus means positive integer. So Pi, precise Pi plus 1 indicates that ith commodity has a higher priority than Pi plus 1. This is the flow model. Our objective is to maximize the flow Xi from each commodity I. We have to maximize the flow. Subject to 3 constants. Constant 1, 2, and 3 are 3 constants. Here AV in, this notation AV in means set of arcs that is incoming arc to node B. Similarly, AV out means set of outgoing arcs from node B. And a new Pi denotes the bottleneck capacity of the path P. So first equation is about first equation in the first sum shows that there is total outflow from node B, and second sum is about total inflow to node B. That must be GI for the source Si, because at the source there is no incoming arc, only outgoing arc. So second sum will be 0, obviously, so it becomes a GI, positive value. Similarly, at the sink, it becomes minus GI because at the sink there are no outgoing arcs, only incoming arcs are there. So first sum will be 0 and value becomes minus GI. And at intermediate nodes, what values in, that values out at the intermediate nodes. That's why it becomes 0. That is called flow conservation. And the question is about capacity constant, which means that total flow in each arc is bounded by its capacity. And third question is about the prioritization of the commodity. Here XDI means flow on arc E with commodity I. Right in the sense shows that first priority is for I equals 1. So new PR1 means the bottleneck capacity on the arc commodity 1 is given first priority. And afterwards, if any residual capacity on the arc is left, then the priority is given to second commodity. And afterwards, if still there is residual capacity, then the priority is given to the third, and so on. To solve the problem, here is an algorithm. Our input is given at n, and in the first step, we prioritize the commodity as we discussed previous. And the second step, we give the set inclusions, taking capital S1 as a set of source of first resource S1, capital S2 for taking two S1 and S2 set of two sources, and so on. And a third step, what we use is using the algorithm of Minica, less-max algorithm of the, together with our priority function equation number 3, as we discussed previous. And our output is prioritized multi-commodity flow in the given network N. This is theorem about the correctness of this algorithm. We use two steps on feasibility and optimality. Algorithm step 1 and 2 can be solved in constant time because step 1 is about the priority for each commodity, and second one is the set inclusion, so that can be solved in constant time. And in step 3, equation 3 is used to give the priority for the commodity on intermediate arcs, which can be solved in order of n times. And the less-max algorithm of Minica can be solved in polynomial time. That's why the theorem is feasible. Similarly, for optimality, as step 1 and 2 are dominated by step 3 of the algorithm, and step 3 is gives the optimal solution. That's why our algorithm provides the optimal solution. This is an example. The first figure is as similar to previous one, which is a multi-commodity network having 3 commodities. Commodity 1 translates from S1 to T1, whereas commodity 2 from S2 to T2, and commodity 3 from S3 to T3. Let's talk about the commodity 1. First commodity translates from S1 to T1. It has 2 parts. One is direct from S1 to T1 with capacity 3, and another part is there S3 B T1, S1 B W. So 2 parts are here. In the second part, we can see the arc VW is common arc to these 3 commodities. So while sending the flow on this arc, we have to give priority to the commodity here. First priority is given to commodity 1. So we can see the bottleneck capacity of S1 BW T1, 6, 11, and 4. Minimum of 6, 11, and 4 is 4. That's why priority is given to commodity 1 with a flow value 4. After that, in RTV, again, residual capacity is left by 11 minus 4, that is 7. So for second commodity, the bottleneck capacity will be the minimum of 5, 7, and 7. So that is 5. So second commodity translates 5 units from S2 to T2. Still again, there we can see 2 units of capacity is left in UV, so that commodity we can translate only 2 units from S3 BW T3. So total flow, what we can translate from source to the sink for each commodity is, for commodity 1 7 units, commodity 2 5 units, and commodity 3 is 6 units respectively. So these are the major differences I have used in this work, and thank you so much.
Okay, thanks very much for all the presenters and all the listeners. And it's a 1 hour's presentation. We study a lot from all of the authors. Thanks all very much. And time is up, and I need to say goodbye and thank you all very, very much, so we can communicate with each other according to the email. Thank you. Thanks for all your work.
Thank you.